In the last video, we talked about these two examples, one of a car running into a brick wall like you see here, another stopping your car over 10 seconds, and we established that if we calculate the impulse required for both of them, even though you might want to think that it's much a greater impulse to run into a brick wall, we actually proved to ourselves that both of those cases have the same exact impulse. It doesn't matter how long it takes to go from one velocity to the other. As long as the initial and final velocity are the same, which means the change in momentum is the same, it requires the exact same impulse. And so the point we came up with was this. There is one specific impulse. With any given collision, with any given change in momentum, there's one impulse. And there was a video that we viewed online, and I'll put the link, I'll put that video on the video page as well, with a Mississippi State professor, and he stated that the impulse in a given collision is exactly the same. It doesn't matter how long the collision takes. Time doesn't matter. And so what that means to us is that in that JFAT equation, J equals F times delta T, force and time are going to balance each other out to produce the impulse. And here's what I mean by that. There's many situations that we can think about to illustrate this. One of those is this car situation where you run into a brick wall or stop over 10 seconds. You can also think about the situation we talked about in class where you throw an egg and the person over here is going to try to catch it. Okay, and you probably know that in order to catch the egg, you kind of have to cradle it a little bit. You have to move your arms with the egg, with the motion of the egg, so that it doesn't break. You can also think about a person driving a car, and if you have an accident in a car, the airbags will deploy, and you will then hit the airbag. Obviously, the point of an airbag is to save your face. Okay, so that you don't break your face. In all of these situations, this equation, J equals F delta T, comes into play. As I said already just a minute ago, the J can't change. In any given collision, there's an impulse that's required to make that collision happen, to change the momentum. So, for instance, in the car example, there's a 70,000 Newton second collision that is required. That cannot change. But if you think about it, in all three of these examples, what does change is the time. In the car example, you stop in 0.4 seconds versus 10 seconds. That was the only thing that changed. Nothing else did. With the egg example, if you cradle the egg, that means you give the egg more time to come to a stop, versus if you allow the egg to hit your hand and you don't move your hand. That means the egg will come to a stop almost instantaneously. So time changes here as well. With an airbag, if you think about if the airbag didn't deploy and you hit the steering wheel itself, your head would come to a stop almost instantaneously, versus when you hit the airbag, your head actually has some time to move through the airbag slightly before it actually comes to a stop. So with this instance as well, you are simply changing the amount of time available for that impact. And again, you can think about many numbers of examples that go along the same lines. The point is this: if we can increase the amount of time required for any given collision to take place, the cool thing about this equation is that by increasing the time, that means we can actually decrease the amount of force that is applied in the collision. In other words, force and time are inversely related to each other. If time increases, force will decrease, and vice versa. If time decreases, the force then must increase in order to bring about the same impulse. Remember that this number must stay the same, and these two numbers can go back and forth with each other to produce that same impulse. This is the reason why it's no big deal to stop your car over a period of 10 seconds, even though it requires the same exact impulse as if you're running into a brick wall. Because you're doing that impulse over a longer period of time, that means that you can apply a lesser force, and that lesser force applied for a much longer period of time will bring you the same momentum or the same impulse, which brings you also the same change in momentum. So that's the main point to bring home about impulse, is that if we can increase the amount of time that it takes for a collision to take place, then it's possible to decrease the force, which is a really, really important thing to happen in any collision involving humans, because that means we can possibly save injury and save life. So just to check to see that you understand what we've been talking about, I want you to read these 4 questions to yourself with this scenario. This is involving landing, if you're jumping, landing with your knees bent versus your knees locked. Probably something you've been told all your life by maybe an elementary school PE teacher or your mom. Really important if you tried to jump off your roof when you were a little kid like I did. But pause the video right now, read these questions, and see if you can answer them for yourself. Alright, hopefully you remember our conversation from before that if they each have the same change in momentum, that means that they're also going to have the same impulse. The impulse is the same because the impulse is equal to the same change in momentum. In both cases, you're moving at some speed before you hit the ground, say 10 meters per second, and after you hit the ground, you're going to be still, your speed is going to be 0. So that's the same change in momentum, which means it's the same impulse. The larger force, however, is felt when your knees are locked. And you know that before you even walked into my class, because if you ever jumped off your roof and landed with your knees locked, it probably didn't end up too happy for you, because force equals pain. Higher force is with your knees locked. Which one had the longer time? Well, when you land with your knees bent, it takes longer for you to actually come to a stop once the impact has begun. And again, because of our conversation about impulse, if we can increase the amount of time for the impact to happen, then that means you can decrease the force, and that's why you want to land with your knees bent, because you'll save your knees. So force and time are related inversely. If one goes up, the other goes down, vice versa. Now, I said that the impulse can't change, and that's only half true. Sometimes we want to change the impulse. For instance, if you want to hit a home run, if you're playing baseball, you don't want to have the same impact. You want to be able to increase the impulse, because the greater impulse you can have, that means that's a greater change in momentum, which means it's more likely that the ball's going to go farther. And judging from the equation, there's 2 ways to increase the magnitude of the impulse: increase the force and increase the time. Most likely what you're going to do, especially in the case of baseball, is to increase the force. Okay, if you increase the force, that'll increase the impulse, which causes the ball to go farther. Pretty simple. Alright, let's look at some practice problems now. These 2 practice problems are in your notes. I'm actually going to run through the second problem with you first, because the second problem specifically involves change in direction, and direction in terms of positive and negative is still going to be very, very important with these types of problems. So in this problem, we have a tennis ball. The mass is 0.25 kilograms. It's traveling towards a racket at 12.2 meters per second. Its hit and its return speed is 14.2 meters per second. It tells us that the ball is in contact with the racket for this amount of time, and it wants to know how much force is applied. We're going to still be using the guess method for all of these problems, and it's a really important thing to be able to understand how to do. Really surefire way to do these problems correctly. So here's my first number. That's the mass, 0.25 kilograms. That's one of my givens. Then I have a couple of speeds here, and I have to decide which one is the initial speed and which one is the final speed. In many of these problems involving a collision, collisions cause change in speed, so we're going to have an initial and a final speed. And usually what happens is that there's an initial speed on one side of a collision and then a final speed on the other. Okay, so in this case, it's the tennis ball colliding with the racket. This is the speed before the collision. This is the speed after the collision. Now, I mentioned direction. It's really important, and I probably got ahead of myself. It's important to draw a picture with many of these problems, if not all of them. In this case, if the ball is headed toward the racket, obviously, if you hit the ball, it won't continue moving toward the right like it was here. It's going to go back in the opposite direction. It will change direction, and the way I've drawn the picture now means that the return speed, the final velocity, had better be negative, because it's going back to the left. If you don't make it negative, it won't turn out right. Now, there's nothing inherent about this problem that makes me draw the picture this way. I could have reversed the picture, but the point would have still been the same. One of these two speeds would have been negative. As long as one of them is, you'll be okay. So don't forget about direction. All right, so I have mass is one of my givens. I know that this is the initial speed, 12.2 meters per second. I know that the final speed is going to be negative 14.2 because it's coming back the other way. They tell me the time, which is 0.012 seconds, and they want to know the force that's applied. All right, there are my givens, there's my unknown, and now I'll pick my equation. Not too hard to do, because you pick the equation the same way we always have in class. You look at what you're given and you find the equation basically that has all that stuff in it. Well, the only equation that has all of this in it, that relates all of it, is the impulse momentum theorem. Okay, so this is where we'll begin to use that. And also I'll give you a trick here in a second about the impulse momentum theorem. If you are given information about one object only, and there's a collision going on, it's obvious that we've got impulse and momentum and things like that. And if we're given information about only one object, which is true in this problem, this is probably where we're going to be going. If you're given information about two objects, that's going to be something else. That's the conservation of momentum, which we'll talk about later. So we start with the impulse momentum theorem, and the first question I ask myself is, what are they asking for? Well, that's the force. So the term that has force in it is definitely going to be part of my equation, no question. F delta t equals something. And the other part is found by looking at what I'm given. I'm given masses and velocities and a time. Well, time is already in this. Masses and velocities are here. So the other part is going to be m times vf minus vi. So there's the e part. The substitute and solve for the guess method. Force is what we want to know. Time is 0.012. The mass is 0.25. Final velocity is negative 14.2. Initial velocity is 12.2. Remember that it's final minus initial. Final minus initial. If you work out this side of the equation, I think you get negative 6.6, and that equals F times 0.012. The last step of this equation will be to divide by, I don't know why I put that there, divide by 0.012. And you will come out with a rather large force of negative 550 newtons. Small tennis ball, big change in momentum, requires a fairly large force. And notice that this force did come out negative. And if we look at our picture, I could have drawn this earlier, probably should have. It may be obvious to you, but in order to get this ball to change directions and go to the left, I've got to apply a leftward force. So I could have drawn this at the beginning to tell myself, hey, I should be expecting a negative force in this case, which is what we got. All right, so this problem is to highlight the fact that direction is extremely important with all of these problems. All right, I want to leave you for a second to do the first practice problem. Work on that for a minute, see what you can get. Pause the video, and I'll come back in a second and work it. All right, let's work this one the same way. Guess method. I know the mass is 0.4 kilograms. This football was sitting on a tee. It was kicked. The kicking is the collision, so there's got to be an initial velocity before the collision and a final velocity after the collision. Well, before the collision, that ball was sitting still, so the initial velocity had to be 0, and once it is kicked, it has this speed. So that's going to be the final velocity. There is no change in direction. And they're asking for the impulse. What impulse did it receive? I have no other unknowns, or no other givens rather, and impulse is J. J is what they want. As far as the equation, once again, I'll start out with the impulse momentum theorem because that's where all of this is contained. So Jfat equals delta rho times mass times final minus initial velocity. J is what I'm looking for, so J is going to be part of the equation. And then once again, mass and initial and final velocity are what we have. So that's going to be the second part of the equation. Not worried about this term, not worried about this term. Plug in numbers. Mass is 0.4, final velocity 12.4, initial velocity 0, and pretty much all you're doing is multiplying 0.4 times 12.4. If you do that, can't remember what I got, 0.4 times 12.4 gives us 4.96. That's right. So the impulse is 4.96, and that can be Newton seconds, or technically could be kilogram meters per second. Either way, that one's probably more correct with this one. Impulse of 4.96.